Hello chemists, this is Ms. Placino and you are watching Screencast 1.7 on isotopes and atomic mass. In today's lesson we're going to talk about what isotopes are and the impact they have on the average atomic mass of an element. If you haven't done the reading yet for this lesson, you really should pause the video, go back and do the reading first. Let's take a look at the do now. Boron has two naturally occurring isotopes, B10 and B11. Which is more abundant? Explain your answer. Alright, so just to review some stuff that we talked about during Screencast 1.6. We say B10 and B11. The B, of course, represents the element boron. The 10 and the 11 are the atomic mass of that atom of boron. So one has an atomic mass of 10, one has an atomic mass of 11. And our job is to try to figure out which is more abundant. And just with the information we have in front of us, there's really nothing more you can do than guess. You need to pull in a third piece of information, and it comes from your periodic table. We talked about what all these numbers, or at least what some of these numbers represent in Screencast 1.6, but just to quickly review, this number at the bottom, the 5, this is our atomic number. And the atomic number is the total number of protons that are present. So remember, if it has 5 protons in its nucleus, it has to be boron. It's impossible to have a boron atom with 6 protons in its nucleus. That changes the identity of the atom. This number up top, 10.81, that is our atomic mass. More specifically, it is our average atomic mass, and we'll be talking about that a lot more in today's lesson. So we're told that boron has its two naturally occurring isotopes, B10 and B11. I'm just going to draw a little number line. So a mass of 10U and a mass of 11U. And we're told that the average atomic mass is 10.81U. So whether you want to visualize it on a number line, or if you want to just think about, okay, I've got 10 versus 11, if you compare that to 10.81, you should come to the conclusion that the boron isotope that is most abundant is the one that has a mass of 11U. And if you were to go online and look up the relative abundances, we'd see that roughly 80% of boron atoms have a mass of 11, and that leaves the remaining 20% to have a mass of about 10U. So again, we can tell which one is more abundant because when we look at the average atomic mass, that's just those two isotopes, whichever isotope the average atomic mass is closest to will be more abundant. All right, let's go talk a little bit more about what isotopes are. So in these pictures, I've got the protons and neutrons that are present in 3 different atoms of carbon. And if you were to really inspect and look closely, you'd see that the total number of red circles, which represent protons, are the same for each of these carbon atoms. There should be a total of 6 protons in each of the carbon nuclei. Feel free to count them if you'd like. And just by looking at the pictures, you can see that the number of black circles, or the number of neutrons, change. As a result, the atomic mass changes. It goes from 12 to 13 to 14. We can figure out how many neutrons are present by taking atomic mass and subtracting atomic number. So 12 minus 6 would tell me that we've got 6 neutrons in this first one, 7 neutrons in the middle one, and then 14 minus 6 gives me 8 neutrons in the last one. Carbon 12, 13, and 14 are what we call isotopes of one another. And all an isotope is are atoms of an element that have the same number of protons but different number of neutrons. And as a result, we're going to see different atomic masses. As you might remember from lesson 1.6, atomic mass is equal to the number of protons plus the number of neutrons. All right, and carbon 12, 13, and 14 will have very, very similar properties. In fact, they'll be identical with the exception of one, and that is radioactivity. We'll be talking about that more later this school year. So one of the big things that we're going to do today is take isotopic information and try to figure out what the atomic mass, or the average atomic mass more specifically, of an element would be. And in order to do that, we need to know what the isotopic abundance, or relative abundance, of each of the isotopes are. All we mean by that is the percentage of isotopes of an element. So basically, what percentage of them are going to be at the different masses. We use only naturally occurring isotopes, and the lab scientists can put together isotopes of all different sorts of masses. We're not going to worry about those. We'll only concern ourselves with naturally occurring isotopes. For example, chlorine has two major isotopes, chlorine 35 and chlorine 37. So if you look here, that's giving you a very precise mass of that isotope. We call it chlorine 35 and 37 because it's pretty darn close to 35 and 37U respectively. This number underneath, the percentages, this is our isotopic abundance. So this is telling us if you had a sample of chlorine atoms, on average about 76% of them are going to have a mass of 35U, and the remaining 24% will have a mass of 37U. And again, what we want to figure out is how to use that data to determine the average atomic mass of an element, in this case chlorine. Go ahead, pause the video, see if you can figure it out. Alright, so let's take a look at how to do this. Basically, what you want to do is take the mass, multiply it by the abundance. I'm going to abbreviate that for one isotope, and I'm going to take the mass times the abundance for the next isotope. You can imagine if I had a third isotope, I could add that in, oops, so on and so forth. I'm going to divide all of that by 100 because we've got our abundances in percentages, and that should be equal to the average atomic mass of that element. So let's go ahead and give that a shot. And I'm going to use the really precise or very specific mass measurements to hopefully get me better answers. So I know that chlorine 35 actually has a mass of 34.96885 U, and I know that there's a relative percentage of 75.77, and I'm going to add that to 36.96590 U times its relative abundance, 24.23. Definitely want to grab a calculator for these. I'm just going to cut off my numbers so we don't have too many things to keep track of. I'll just go to 4 total digits. We won't worry about significant figures at this point in the game. Those will come up later this semester. I'll add those together to give me 3546U. Last step is divide by 100. Really just move the decimal point over 2 places and I end up with 35.46U as the average atomic mass for chlorine. We can check and see if that makes sense. Okay, yeah, I've got chlorine 35 and chlorine 37. Chlorine 35 is clearly more abundant, so my average molar atomic mass should be closer to 35 AMUs, and it absolutely is. You also have the built-in check of looking at the periodic table, and you'll see that it's like 35.45 is what they have on the table. We are pretty darn close, and I bet if we took our stuff out to more places after the decimal point and didn't round, we could probably hit it right on the nose. So that's really the big take-home lesson from today. You've got to be able to take mass and relative abundance or isotopic abundance information and figure out the average atomic mass of an element. We can make things a little bit more challenging, and this is really above and beyond the scope of an introductory level chemistry course. So I can tell you that rubidium has 2 naturally occurring isotopes. First one is rubidium 85. The other one is rubidium 87. And these masses, as you might have guessed, are the very precise masses. What are the relative abundances of each isotope? In other words, what percentage of all rubidium atoms are Rb85 and what percentage of them are Rb87? This is more challenging, so pause the video, think about it, try it out, and see what you come up with. Okay, before we can do much of anything with the information we're given, there's a third piece of information that we need to go look up. Hopefully you figured out that it is the actual atomic mass, average atomic mass of rubidium. So this number comes directly from the periodic table. From there, I know that I can take mass times abundance plus mass times abundance to get to my average atomic mass. I need to alter that a little bit, and I'm going to do that by taking 84.912, and I'm going to skip out my units because I don't have a ton of space, times x, because I don't know what that relative percentage is just yet. I'm going to add that to 86.909. And we know that percentages can be converted into decimals. So I'm going to go 1 minus x. So I know percentages have to equal 100. Again, I've gotten rid of the percentage, so I divide everything by 100. So x and 1 minus x better add up to equal 1. And I know the average atomic mass of rubidium is 85.4678. I can go through and do the math. I end up with 84,912x minus 86.909 minus 86.909x is equal to still 85.4678. I can go ahead and simplify down further, so I'll kind of cut to the chase. Negative 1.997x is equal to negative 1.4412. Solve for x, and I come up with x is equal to 0.72, and we'll just cut it off there instead of taking more places after the decimal point. So I know that basically one of my percentages has to be 72%, and that leaves my other percentage to be 28%. Now that you're done with all the math, you've got to do a little bit of thinking just to figure out which is my more abundant isotope. This is something we tackled at the very beginning of the lesson. My average atomic mass is much closer to rubidium-85 than it is to rubidium-87. So I would go ahead and assign rubidium-85 the roughly 72% relative abundance, and the rubidium-87 must be the 28% abundance. And if you were to go online and look up the isotopic abundance for rubidium, you'd see that we're pretty darn close with those numbers. Nice work. All right, so you've got space in your workbook to write a 60-second summary. Again, just give me maybe 2 sentences or so to summarize the key concepts from today's lesson. Make sure that you're taking the time to do the extra practice problems that you've got on the page. The stuff that we did on the previous slide, determining the relative abundance, that's advanced, and I'm not going to ask you to do that on something like a quiz or a test, but it is kind of just fun to see what you can do with some really simple algebra. One thing that you are going to be held responsible for is determining the average atomic mass of an element when given mass and relative abundance data. All right, hope this lesson was helpful, and we'll see you tomorrow in class.